I leave home for a few days and look what happens. This won't take long.
This is Professor Nodal Science, and today I want to discuss spherical harmonics on rigorous quantum mechanics.
And how the math is a direct analog for the vibrational modes of the spherical Earth. And why it's so important to all the rest of my research. And hey, let's check out Coral Castle!
Spherical harmonics are the eigenfunctions of orbital angular momentum in quantum mechanics. As such, they feature in many problems, but most importantly, they feature in the hydrogen atom. We're going to dissect the mathematical form of the first few spherical harmonics. We're also going to visualize them. We also have a link in the description to a Jupyter notebook which has some Python code to generate the spherical harmonics, so I encourage you to take a look and see what it does. The main reason why we study spherical harmonics is that they play a central role in the theory of orbital angular momentum in quantum mechanics.
The spectrum of the vibrating string consists of multiples of the fundamental frequency f0. These specific modes of vibration can be classified according to the number of nodes. Let us consider the simplest mode of vibration having two open ends. It has one node in the middle and one antinode per each of the two edges. Let us now bend this vibration to form a semicircle. Rotating this semicircle around the z-axis will result in a sphere. There is an azimuthal nodal line at the equator of the vibrating sphere. We can perform the same steps for the following resonant frequency, which has two nodes. Let us bend the vibration to a semicircle, and again, let the semicircle rotate around the z-axis. This results in a vibrating sphere having two azimuthal nodal lines. We can repeat this on and on. Bending and rotating the vibration with L nodes results in a vibrating sphere with L nodal lines. By definition, these sphere vibrations are rotationally symmetric. They are also their own reflection. Positioning the mirror plane exactly in the middle will result in an identical mirror image. L specifies the total number of azimuthal nodal lines. There is no nodal line for L equals 0. There is one nodal line for L equals 1. However, this exceptionally symmetrical vibration does not reveal the full range of possibilities, because we can also rotate the nodal line on the sphere. Let's rotate that nodal line to the right, or reflect it to the left. There are now two new modes of vibration on the spherical surface with one nodal line. Those are vibrations with an azimuthal nodal line that is rotating clockwise or anti-clockwise. In the case of two nodal lines, there is an option to rotate not just one, but both nodal lines to the right and reflect their image to the left. In the case of three nodal lines, we can rotate first one line, then two, then all three nodal lines to the right, and reflect their image to the left. There are thus 2L plus 1 potential modes of vibration on the spherical surface with L nodal lines. We can generate any number of basic modes on the two-dimensional spherical surface by adding and rotating nodal lines, starting from the simplest vibration.
And why it's so important to all the rest of my research. And hey, let's check out Coral Castle!
This is the eigenvalue equation for the squared angular momentum, and this is the eigenvalue equation for the z component of orbital angular momentum. The L squared eigenvalues are labelled by the quantum number L, and it can only take non-negative integer values, and the Lz eigenvalues are labelled by the quantum number M, and for a given L, M can only take one of the values minus L plus 1, and so on, all the way to L. However, today's focus is not on the eigenvalues, but instead on the eigenstates that are shared by both L squared and Lz here and here. These eigenstates are the so-called spherical harmonics. We can write the spherical harmonic YLM of theta phi as equal to this log prefactor multiplied by a phase factor and then this other long expression involving sines and cosines. Then we can write the spherical harmonic YLM as equal to this long prefactor multiplied by the phase factor and everything multiplied by a function PLM of the cosine. These functions P here are called the associated Legendre polynomials. But today we are not going to explore them any further, so if you're interested in learning more about them, I encourage you to check them out elsewhere. The visualization of spherical harmonics is something that you will often encounter because spherical harmonics feature in a variety of quantum systems, most importantly the hydrogen atom. We first need to note that the spherical harmonics depend on the two angular variables theta and phi. Let's consider a general point here at a position given by the vector r from the origin. And in spherical coordinates, we describe the position of this point with a set of three numbers. The distance between the origin and the point, r, the angle between the vector r and the third axis, theta, and the third is built by first projecting the vector r onto the horizontal plane, measuring its angle with respect to the first axis, and we call it phi. R is the length of a vector. It can only be 0 or positive. The angle theta runs from 0 to pi, and the angle phi from 0 to 2 pi. Now this here is an example of how we will plot the spherical harmonics. And now all that matters is how we are representing it. We're not going to plot the coordinate axes in general, but for now, there are these three here and they should help you as a reference. The color shows the value of the function. Red regions show the angular positions where the function takes large positive values, and the blue regions show the angular positions where the function takes large negative values. For intermediate values, we plot the function with a color scale that goes from positive red to negative blue through 0, which is white. In this particular example, both the North Pole here and the South Pole hidden behind here are both white, which means that the function is 0 at those positions. And in fact, the function is 0 along a whole great circle that unites the two poles. And to understand these plots better, we will often rotate the coordinate axes like this, allowing us to see the value of the spherical harmonic in all angular directions. The spherical harmonics are labeled by the quantum numbers L and N. As L is associated with the magnitude of orbital angular momentum, we will use this as the main quantum number from which to build the spherical harmonics. So let's start with L equals 0. This implies that M is also 0. The corresponding spherical harmonic is therefore... So overall, the spherical harmonic y00 is equal to the constant 1 over square root of 4 pi. This here is a plot of the y00 spherical harmonic. It's trivially a solid uniformly red sphere. The color is uniform because the function is a constant. Let's now consider L equals 1. There are three possible values of M, -1, 0, and 1. So let's start with L equals 1 and N equals -1. Start with a prefactor here. We can write it down inserting comes -2 sine theta. The spherical harmonic y1 1 is given by this prefactor, this phase factor, and all multiplied by sine theta. We'll also separate this expression into its real part and its imaginary part. These plots show the y1 1 spherical harmonic. The top diagram shows the real part, while the bottom diagram shows the imaginary part. Let's start with the real part, which is given by this term up here. Remember that the angle along the horizontal plane is measured by phi, and that phi runs from 0 to 2 pi. We see that the phi dependence is fully captured by this cosine term. For the phi dependence, the real part of the y1 1 spherical harmonic exhibits a full cosine oscillation from positive to negative and back to positive, and pictorially we get red, white, blue, white, and back to red. Here we see that the theta dependence is fully captured by this sine term. We can finally make these diagrams rotate to appreciate the full angular dependence. It's not the easiest to get your head around this type of plot, so I recommend that you take your time until it becomes completely clear. Let's now look at L equals 1 and M equals 0. We have the spherical harmonic y10. We get the prefactor square root of 3 over 4 pi times the cosine of theta. This here is a plot of the y10 spherical harmonic. We see that y10 does not depend on the angular variable phi, which implies that the spherical harmonic looks the same in all directions within the horizontal plane. y10 does depend on theta through this cosine function. At the North Pole, where theta is 0, the cosine takes the maximum value, hence the red color. Then on the horizontal plane, corresponding to theta equals pi over 2, the cosine vanishes. This is indicated by the white band. At the South Pole, where theta is pi, the cosine takes its maximum negative value. We get the blue color. Again, as there is no phi dependence, these results are true along any phi direction. Do spend as long as you need to really make sure that this plot makes sense. Finally, let's look at L equals 1 and N equals 1. y11. We get this prefactor, this phase factor, and all multiplied by sine theta. We can separate this expression into a real part and imaginary part. This here is a plot of the y11 spherical harmonic. The expression is really quite similar to the spherical harmonic y1 1. This means that the only difference in the plots is that the real part is the negative of the real part of the y1 1 spherical harmonic. That one we had red in front and blue at the back. Whereas here, we have blue in the front and red at the back. We can again make them rotate to better appreciate the full angular dependence. As a summary, we have here the 3 spherical harmonics. It's not really trivial to get your head around these plots, so again, do take as long as you need to make sure that you are absolutely happy with the plotting. So let's next consider L equals 2. For this value of L, there are 5 possible values of n. -2, -1, 0, 1, and 2. The mathematical form of the spherical harmonics is analogous to that of the previous 2 examples. These here are the 5 spherical harmonics for L equals 2, but to fully appreciate their angular dependence, we can also make them rotate about the vertical axis, starting with y2 -2, then y2 -1, y2 0 doesn't have a fine dependence, so it looks the same at any angle about the vertical axis, and we can also make y2 1 rotate, and finally y2 2. We could of course go on and plot additional spherical harmonics. Here I have the L equals 3 spherical harmonics. We can again make them rotate for better visualization, starting with y3 -3, then y3 -2, y3 -1, again the y3 0 spherical harmonic is purely real and doesn't depend on phi, so zero directions. Moving to y3 1, we can again make it rotate. The same for y3 2, and finally for y3 3. We've generated all of these figures using Python, and you can have a go yourself plotting spherical harmonics by following the link to the Jupyter notebook in the description. Overall, I hope you will agree that these diagrams have a rather captivating beauty about them. To finish, I just want to point out that you will encounter spherical harmonics depicted in a variety of ways. I personally think that the approach that we've taken today is particularly clear because it really highlights the angular dependence of the spherical harmonics by plotting them on the unit sphere. We show this alternative approach in the bottom row.
There. That should give us enough